Now it's on? Okay, good. How do I wear this? Yeah, yeah, that's good. Is- Okay, should we start? Right, so hi everyone. My name is Srujan. I'm a fifth year grad student in Marco Lonchar's group at Harvard. And today I'll be talking about our work on strain engineering of silicon vacancy centers in diamond cantilevers. So essentially, in this talk, what I'll describe is our recent work in which we uh, look at nanofabricated diamond cantilevers that are, say, about a micron wide, about 20 microns long, and we look at single silicon vacancies inside these cantilevers. For those of you who don't know what SIVs are, they're basically point defects in the diamond lattice where you replaced a carbon atom or two carbon atoms with one silicon atom. And we're studying this one silicon atom as we apply strain to this cantilever by bending it. And as we apply strain, the electronic levels of this defect shift, and we basically measure changes in the optical and spin properties of this defect as a function of this strain. So this is basically what I'm going to talk about for the next half an hour to 45 minutes. So what is the motivation for this work? The motivation in the broadest sense is this idea of quantum networks, where we basically want to build networks of quantum systems. So they're basically these red boxes connected by arrows. It's as simple as that. Um, each of these quantum nodes basically has what we call qubits that are entities in which you store quantum information. And these boxes can be as far apart as tens of kilometers. And if you find a way to get these to interact, then you have a quantum network. And this is important because linking up qubits this way can allow you to build a large quantum system, which is kind of the essential ingredient for quantum communication and computing, which we know can improve classical technology in many ways. So quantum communication, some of you may have heard of, can enable fundamentally secure communication in a way that classical communication cannot be. And quantum computing can allow you to solve problems that are intractable on classical computers. So let's dig a bit deeper and talk about what are the ingredients of a quantum network. So quantum nodes are usually comprised of at least one qubit or a few qubits, and these qubits are encoded in atomic systems. So atomic systems can basically be atoms, natural atoms. So these have been the workhorse of the field of quantum optics. So single atoms like cesium and rubidium are trapped by laser beams. And then you basically encode information in the internal levels of these atoms and use them as qubits. Over the last couple of decades or so, there's a new class of quantum systems that have emerged in solids. And these are what we like to call artificial atoms. There's quantum dots, there's superconducting qubits, and today we'll be talking about defects in diamond or diamond color centers. So these systems have their individual advantages and disadvantages. So natural atoms, because you are isolating single atoms, they don't have any much of an environment to talk to. So their optical and spin properties are very pristine, which makes them in some ways the textbook quantum systems. However, these systems are challenging to work with. Even to trap, if you've looked at any of these experimental setups, even to trap a single atom, you need setup the size of an optical table to do it. So scaling this up to build this kind of network where you have many qubits interacting is going to be challenging. Okay. Um, on the other hand, with these artificial atoms, the scalability comes more naturally. You can make many of these pretty easily by nanofabrication technology. But keep in mind that these are sitting inside a solid matrix. So they're sensitive to everything that's happening in the solid state environment, such as lattice vibrations, charge fluctuations, fluctuating magnetic fields. So there's a lot going on in solids, and these optical and spin properties are perturbed um, by the solid state environment. So the question that the field is trying to answer now is, can we find a system that has both these advantages, that has good optical, whose internal levels are well behaved, and at the same time allows you to scale up to a network with a large number of qubits. And hopefully by the end of this talk, I can convince you that the silicon vacancy defect that we're looking at in Diamond is a step in this direction. Okay? Now, the next question is, what is this channel? Now, if these boxes are tens of kilometers apart, and if you want to send information from one node to another node, the most natural way to do it is the way you send classical information today. You do it in optical fibers, right? You use light, because light is a good way to transmit information over long distances. So you usually use photons that are generated from these atoms. Fortunately, these atomic systems have optical response in addition to long-lived internal levels, such as spin states that can store this quantum information. You can have an optical response that you can use to transfer this information into the channel and to the next node. So let's start talking about the artificial atoms that we study at Harvard as part of CIQM. So these are these diamond color centers. So what are these color centers? They're essentially point defects in diamond. And I said artificial atoms, but in fact, they occur in natural diamonds. We do know that natural diamonds come in a lot of beautiful colors like these. And these are caused by these color centers, which are basically point defects, such as this one, the nitrogen vacancy, which is the most well-known color center in this field. So why is it that diamond in particular can come in so many colors? Why not silicon? And the answer is that diamond, as a solid-state physicist, you know that it's a wide bandgap material, right? So when you have an impurity like this inside the diamond lattice, say 2 carbon atoms are kicked out and there's a nitrogen atom, the electronic levels of this defect can sit within the bulk bandgap of diamond. And when they're optically active, the light that's emitted by them can escape the diamond lattice without absorption, right? So if you take a look at the fluorescence spectrum of these defects, this is an example of the NV fluorescence spectrum, you see something like this, typically, where there's a sharp peak, and then there's a broad shoulder. So the sharp peak arises from a narrow atom-like electronic transition. So these are, say, 2 levels of the defect, and there is basically what you would see in atomic systems. And this is what's called the ZPL, or the zero phonon line. And the reason it's called that is because you're in a solid-state environment, your transition can also be assisted by lattice vibrations. So if you have a bit of help from lattice vibrations and a bit of optical scattering, you can get this kind of emission at a different color, and that's what makes up this big shoulder. Now, the important thing to note is that this is the emission, only the light that's in this zero phonon line that's useful for quantum information applications, because these are atoms that are coherently scattered by the atom, photons that are coherently scattered by the atom, and can be used to encode the quantum information in the spin, say, for example. So this is the most well-studied defect. Most of you may have heard of this. But today what I'm going to talk about is new defects that we've been exploring at Harvard and in a bunch of other labs. And in particular, the silicon vacancy, which kind of looks like the NV, but you've basically kicked out the nitrogen and put a silicon. You still have 2 missing carbon atoms. But because the silicon atom is a bit larger than a nitrogen, it tends to sit in between these 2 vacant sites. And because of that, and you can clearly see between these 2 pictures, one of the important differences between these defects is that these new kids on the block, the SIV and the germanium vacancy, which we've been looking at for the last few months, instead of a silicon, you can have a germanium there. These defects have inversion symmetry. What does that mean? You can invert the defect about the central point where the silicon is, and the defect basically remains unchanged. So that's not true for the NV. It doesn't have a center of inversion symmetry. And it turns out that this inversion symmetry gives this defect very special or very nice optical properties. In fact, it makes the SIV optically closer to being an ideal trapped atom or ion, and that's what I would like to explain now. So how is that? So what are the nice properties that you would want so it would be closer to an ideal trapped atom or ion? So first off, most of the emission fluorescent emission of the SIV goes into the zero phonon line. There's a very weak phonon sideband compared to what you saw for the NV on the previous slide, right? You can pretty much only see a sharp line. So that's 70% of the photons at room temperature. At low temperature, it's even higher. The second thing is that if you have a sample that has lots of silicon vacancies and you pick any two, those two silicon vacancies are optically pretty identical, as in the transition frequencies are quite similar. Say if I have 10 silicon vacancies, it's quite likely that two of them are going to have the same optical line. Whereas for a nitrogen vacancy, I need about 100 to find two that are identical. Or for quantum dots, it's more like 1,000 or none. So that's what we like to call small inhomogeneous distribution. If you pick one of these silicon vacancies, and if you just park yourself on an optical transition and watch that frequency over time, so this is also a big problem in solid-state systems, these optical lines are usually not stable over long periods of time. They tend to wander a lot, jump back and forth. And the reason that happens is, again, because you're sitting in a solid-state matrix, there's all sorts of things happening when you're trying to excite these defects with laser. There's other defects, there's charge traps, there's fluctuating electric fields, mainly, that can cause the lines to wander. But because of this inversion symmetry, these optical transitions of this defect are insensitive to electric fields, to first order. We can talk more about that later if you're interested how. And that makes the optical lines quite stable. You can see that it's wandering, but it's if you look at the y-axis here, this is a few hundred megahertz. For NVs, this tends to be 10 or 100 times worse. And it's important to have your optical line stable if you want to do, say, build a quantum network with these systems. And lastly, it maintains all these nice properties inside nanostructures, which is certainly not true for nitrogen vacancies and a wide variety of solid-state systems. Nanostructures are inherently dirtier than bulk solids because they have more surfaces, more defects, more charge traps, et cetera, that the system that you're trying to study can be sensitive to. So this allows me to transition into the second ingredient for this talk, which is diamond nanoscale devices. And this is sort of the expertise in our group, in Marco's group. So why do we make these nanoscale devices? So most of the devices we make are nanophotonic devices, like this beam that's perforated with holes. So you can see this is called a photonic crystal cavity. What this does is, and you've heard Marco talk about this plenty of times, is it traps light in the center of the structure and allows light to interact with the silicon vacancies strongly. And these kinds of devices are essential to interface your quantum system efficiently to light. So if you saw on the first slide, to basically take quantum information in that red box and put it onto that arrow efficiently, you need an efficient light matter interface. And recently, with these kinds of nanophotonic structures, we were able to show single photon switching and entangle two silicon vacancies. That was up on Science, I think, about last week or so. So in contrast, so this is most of our work, but what I work on and what's the topic of my thesis is a second thrust that we're running in parallel with freestanding devices like these, but instead of using their optical properties, we're going to exploit their mechanical degrees of freedom. This is a freestanding structure. It can bend and vibrate, right? So we're going to use those degrees of freedom and see how they interact with the SIV. Right? So why are we interested in putting SIVs in mechanical structures? For SIVs in particular, are interesting nanomechanical structures because it's known that they have a very large strain response. So the electronic levels of this defect can shift a lot with strain, and this has been measured in the 90s in the early days of color center spectroscopy. In fact, the ground states of this defect respond to strain about 5 orders of magnitude larger than the NV ground state for very fundamental reasons, and we can discuss that later. So what do we want to do with this? So the simplest thing that you can think of is typically, for these solid-state systems, two atomic systems are never exactly identical. So strain is perhaps for the SIV, it's the most natural choice if you want to match the optical lines of two of the emitters. So basically, if you want to make box 1 and box 2 exactly identical and talk to each other, then strain is the way to do that. The second thing, so this is mostly going to be, the direct application of what I'm going to talk about today. But the second thing, which we're also building towards, is to do what's called strain optomechanics. So in that cartoon that I showed in the first part, probably in the first slide, if instead of just statically bending this beam, you use the fact that this is a mechanical resonator, right? This can vibrate, and it is a resonant structure. And when it vibrates, the strain at the site of the color center oscillates at the frequency of the mechanical mode. And you can use this to basically create an interaction between the color center and this mechanical mode. What is this useful for? If you have, say, 2 qubits inside this resonator, then you can basically couple them via the mechanical mode, much like you can do it with light. The physics is very similar. So why would you be interested in doing this with vibrations or phonons instead of photons? The answer is, so if you wanted to do this kind of stuff, it's like, it's unclear why you would want to do it with phonons. You could do it with light, right? But if instead you wanted your red box to interact with, say, a blue box, right? Your red box could be a diamond color center. Your blue box could be a superconducting qubit. These two boxes have very different languages that they recognize. If I take a red photon from this box and send it to this blue box, it's not going to respond, right? Because it doesn't have a natural response to photons. But on the other hand, mechanical vibrations coupled to a wide variety of quantum systems. So phonons the community right now thinks that phonons are the way to get dissimilar quantum systems to talk to each other so you can exploit their individual advantages. So these guys have an optical response, but say these guys are really good for doing information processing. And phonons are a way to connect them. So I've been talking about tuning of electronic levels. So what are these electronic levels? So this is the electronic structure of the silicon vacancy. So if you consider the zero phonon line that I was talking about earlier, and if you look at the zero phonon line of this defect at low temperature, below, I think, like in the range of tens of Kelvin, we do the experiments at 4 Kelvin in our lab. You will find that the ZPL is made of 4 lines that look like this. And the electronic structure that gives rise to this spectrum is this. So you have a ground state and an excited state. They're both separated by about 737 nanometers, which is the mean ZPL frequency. And the ground and excited state both have 2 orbital branches that should be degenerate, but because of spin-orbit coupling, the degeneracy is split. And it's split by about 50 gigahertz in the ground state and 250 gigahertz in the excited state. So in the first part of my talk, I'm going to discuss how we can apply strain and basically tune this level structure. Now, in addition to this optical response, the SIV can also provide a spin qubit. And you know that this is a crucial ingredient for this to act as a quantum memory or be used as a quantum node. If you apply a magnetic field, these 4 levels, each of these levels splits into 2 because the SIV is a spin half color center. So one of these levels is down and spin down, and the other is spin up. All right, and you can encode your quantum information in, say, 2 of these spin sublevels, say on the lowest branch. So this constitutes your spin qubit. And the techniques that we use to control this spin qubit, you can use microwaves like you do with the nitrogen vacancy. But as of now, it's somewhat easier in our setup to just do it all optically. So we use techniques from atomic physics where we basically shine 2 lasers to coherently control the spin. And I'll talk a bit more about this later. So this SIV has very nice optical properties, which is something I stressed on a lot. But one of its disadvantages is that the fact that the spin qubit is not quite as nice as the nitrogen vacancy. In fact, the amount of time for which you can store information in the spin qubit, the so-called coherence time, is of the order of 40 nanoseconds at 4 Kelvin. And if you remember, for the NV, it's of the order of a millisecond, right? So you can quantum information doesn't stay in the spin qubit for very long, and we understand now that it's limited by a thermal process. And In the second part of my talk, I'm going to discuss how you can apply strain to the silicon vacancy to circumvent this thermal process and improve the spin coherence, potentially to the level of the nitrogen vacancy. We're not quite there yet, but we have seen an improvement with strain. All right. So let's move on to the details of the experimental work. How much time do I have? Yes. This is a negatively charged SIV, yes. No, so you have, yeah, it depends on how you look at it. You have five, four from the silicon, one extra, and then you also have one electron each from the six dangling carbons. So this is, I think it's called D3D, D3D, yeah. So it has the trigonal symmetry of the NV, but it also has this center of inversion symmetry. But if you're interested, we can talk more about the electronic structure later. It's quite interesting. Yeah. Um, Okay, so if there are no more questions about the introduction, I'm going to start talking about the experiments in more detail. So the devices that we work with, as I mentioned earlier, are cantilevers. So our chips usually look like this. They're arrays of diamond beams. And if you zoom into one of the beams, it looks like this. Everything that's dark in this SEM image is diamond, and everything that's bright is metal, gold. So what you see here is a diamond cantilever and two electrodes. So there's an electrode on top and an electrode on bottom. And in principle, this is a parallel plate capacitor. You can apply a voltage. There is an electrostatic force between the two plates. And because the structure is free to move, it's going to bend when you apply a voltage. And by exactly dialing in the voltage, you can control the amount of strain in the beam. Okay, so this is the basic idea of this device. The other nice thing is that we have a window in the top electrode because we want to look at silicon vacancies that are inside the beam. So this array of yellow dots is not just a cartoon. We can actually, sorry, I keep messing up going back. We can actually make devices that look like this, where you have a neat little array of SIVs along the beam at regular spacing. And the technique that we use to do this is called focused ion beam implantation, where you basically shoot a focused ion beam of silicon vacancies exactly at the spots where you want to implant it. So you can deterministically position these emitters, which is a big challenge for solid state emitters, but we can now do it with SIVs. And this is done in collaboration with a group at Sandia National Labs. So this is, for those of you who are interested in device fabrication, this is kind of what the scheme looks like. We pattern, so this is the view in which the cantilevers are coming out of the page, okay? We pattern resist, which allows us to etch beams. And the key ingredient to realize these cantilevers is something called angle etching, which was developed by our group. You might have heard Marco talk about this previously. The one thing that we do newly after we make these cantilevers is we deposit metal to realize the electrodes. And one cool thing about the way we do this is traditional liftoff, which is what you would use to deposit metals or pattern metal. But there's really only a single step in which we create a window around this cantilever beam, and we leave a tiny bit of the edges of the cantilever exposed as well. So once you blanket deposit metal on top of the structure, you will realize both the electrode on top of the cantilever, if I go back, you'll realize both this top electrode and the bottom electrode simultaneously in a single step. So they align, self-align by virtue of the fact that you made the mask this way. Okay. Another thing that we can do in our experiment, which was kind of not possible in the 90s version of this experiment that I showed earlier with the old data, is that we can control the strain axis simply by controlling, simply by fabricating these cantilevers along the 110 direction. So we know that the silicon vacancies occur along the 111 axis of diamond. And because of the crystal symmetry of diamond, that means there's 4 identical orientations. But once you fabricate this cantilever and apply strain along 110, you've broken that symmetry. And you've broken that symmetry to differentiate 2 classes of SIVs. There can be SIVs that are perpendicular to the beam, so to speak. So essentially, if this is the cantilever, which is along 110, you can have 2 classes of SIVs that are sort of like that. So that's what I've shown in this first picture here. And in this case, the dominant component of strain, when you apply strain with the cantilever, is perpendicular to the SIV axis. In this case, the SIVs look like they're parallel when you look from the top, but they're kind of like that, right? You can have it either like that or like that. They're both identical. And we do notice that these 2 classes of SIVs actually respond differently to strain. So once you apply voltage, we see that SIVs that are experiencing strain in the transverse plane show this behavior where only the 2 of the 4 outer, out of the 4 transitions, only the 2 outer ones tend to shift, and they shift outward like that, and the 2 inner ones remain more or less fixed. Whereas SIVs that experience an axial component of strain have this large center of mass shift, essentially this behavior in which all 4 tend to move together in the same direction. And based on these 2 responses, we can sort of deconvolve what's going on and build a model for a response to various strain tensor components. So we can predict that when strain occurs exactly along the 111 direction of this defect, that only leads to a shift in this mean splitting between the ground and excited state. So this these splittings delta G and delta E remain unchanged, but it's just the mean zero phonon line frequency that shifts, and that's basically what you see in this picture. So this is okay. But what's sort of more interesting and what's going to be the focus for the rest of my talk is the response to transverse strain that's in the perpendicular direction to 111. And what this strain component does is that it leaves this mean splitting unchanged, but it splits apart the ground and excited state manifolds like this. All right. And what I've shown here is I've plotted the ground state splitting delta G and the excited state splitting delta E as a function of strain on the x-axis. And it shows this behavior where it's quadratic for low strains, and at higher strains it becomes linear. And this can be explained by an expression that looks like this, where the strain quadratically adds to the spin orbit coupling and goes under a square root. This is, for people in atomic physics, this is a signature of a Hamiltonian that looks like this, where strain is on the off-diagonal terms and essentially mixes these 2 branches. Okay, and these are the numbers for how responsive these splittings are to strain. So this is a petahertz, that is 10 to the 15 hertz per strain. So I know it's a weird unit, but the way to think about this is, so unit strain doesn't make any sense, right? Because strain is change in length divided by original length. But if I had, say, 10 to the minus 3 strain or 10 to the minus 4 strain, which is the orders of magnitude of strain that we have, then you can get hundreds of gigahertz of shift, which is what we see. Okay? Are there any questions at this point? Because next thing I'm gonna do is move on and do something useful with this effect. Okay. So if you think about it, this is a very big perturbation to the defect. You started with a ground state splitting that was of the order of 50 gigahertz, and we can increase it to hundreds of gigahertz. In fact, in our best devices, we can push this splitting delta G to as high as a terahertz. So that's, you're altering the energy splitting by almost 2 orders of magnitude. And when you introduce that kind of a dramatic change, you actually see dramatic changes in your optical spectrum. So what we see is that at high strains of the order of 10 to the minus 3, 2 of the optical lines actually disappear. The B line, so we label these A, B, C, D usually in the SIV literature. And these two lines, the second one and the fourth one, vanish. And I'd like to talk a bit about why this happens, and it's fairly simple. And this is sort of a primer for what's going to come next in terms of the spin. So um, what you're doing when you're applying strain and increasing this ground state splitting to massive values is you're affecting the thermodynamics of this ground state. So at zero strain, when the splitting was 46 gigahertz, or let's say roughly 50 gigahertz, um, a useful number to compare that splitting to is KT at 4 Kelvin, which is 80 gigahertz. So what this means is that these two levels are essentially thermalized at 4 Kelvin. You have ground state population that's sort of 50-50 distributed between these two branches. But once you apply strain, thermodynamics tells you that you will basically, at the point where this delta exceeds KT by a large amount, you're essentially going to deplete all the population in this upper branch. And that's the reason you kill these two lines, B and D. All right, is that clear? So thermodynamics tells you why these two lines disappear, but it doesn't actually tell you what is the kinetics of this process. What is the physical mechanism by which these states are thermalizing? And the answer to that actually lies in the strain response model that we measured. Okay, so as I was saying earlier, strain tends to mix states within these two branches. So what that interaction can do is if you have AC strain, so if you have vibrations that are basically resonant to the splitting, then they can effectively drive transitions within these ground and excited state manifolds, right? Where do these resonant vibrations come from? They're just phonons in the lattice, right? So if you're at 4 Kelvin, as I said earlier, you do have an appreciable number of thermal excitations at 50 gigahertz, which is this splitting, okay? And this is something that's been verified additionally by a measurement of these rates, gamma up and gamma down with temperature, which was published by our collaborators in the Lukin and Uletsko groups around about a year ago. So it turns out that these phonon processes have a very important implication for the spin of this defect. So if you go back to this picture that I showed earlier, when you apply a magnetic field, you have each of these levels split into two, okay? And if you just zoom into the ground state manifold, which is what I've shown here, in addition to these two nice spin qubits that you have on each of the orbital branches, now you have a phonon process. We know that there's this process which can basically connect levels that have the same spin but the opposite orbital character. So basically, lattice vibrations, because they couple to the charge distribution of the electrons, they can kick you from one orbital to the other orbital, but they cannot flip the spin. There's no fundamental mechanism by which a vibration can flip a spin, right? So what this means is that vibrations cannot, flip your spin directly, but there is this decay process that is connected to your spin qubit. All right, and it turns out, and it's been proven that it is this decay process, this additional dissipation channel, is what spoils the spin. This is what limits the spin coherence time to 40 nanoseconds. In fact, if you measure these rates, and I'll show you in a bit how to do that, if you measure these rates gamma up and gamma down, you will find that they're actually of this time scale, and that's where this number comes from. But in fact, if you measure what's called the T1 time, the lifetime of the spin, that is of the order of milliseconds, which is what we see for the nitrogen vacancy. Okay, so in a sense, that's good news. We know where this limitation comes from. Now, how do we solve this issue? How do we improve the spin coherence time and make this silicon vacancy useful? Okay, so one way to do that is, so the main culprit for this is thermal excitations, right? So why not go to lower temperatures? Go to 0 Kelvin, right? Or 100 millikelvin, which is what we're going to start doing at Harvard from about December or January. We're getting a dilution fridge, so that'll be quite nice. But perhaps a more elegant solution to this is, why not just increase this strain splitting? Increase the strain splitting delta G such that it's much larger than KT. As I showed you earlier, we can increase this to hundreds of gigahertz or a terahertz, which is way larger than 80 gigahertz, right? And what that would do is it would completely kill this upward process. So if you define your spin on this lower branch down here, right, you kill this upward process, and in addition to that, all the population in the ground state sits entirely in this branch, as I showed earlier. Those two optical lines disappear. So for all practical purposes, your spin is not even aware of these other two levels, all right? So with that motivation, we tried to essentially probe the thermal physics of these two ground states and measure the spin at the same time as we apply strain. So that's what I'm going to talk about for the last part of the talk, right? So let's think a bit more about the rates of these thermal processes, because that's what is going to determine the spin coherence. So naively, you would think that if I just kept increasing this delta, I'm depleting thermal excitations that are resonant to delta, and the rate of the process is going to go down. But it turns out that the story is a bit more complicated. So what I want you to think about right now is the process gamma up, where population is kicked from level 1 to level 2. So this is a sort of a toy physics problem where you have a two-level system that's coupled to thermal excitations, okay? And if you want to calculate this rate gamma up, and you can do this using Fermi's golden rule, you will find that the expression for gamma up has two factors. One is your Bose distribution for the thermal excitations that it can couple to. This is what you expect. And that's what I was talking about earlier. But in addition to that, you also have this delta cube term that appears before, which corresponds to the density of states of phonon modes in the lattice. So if you increase the energy splitting, you're going to exponentially deplete the thermal excitations that can couple to your defect, but you're also going to increase the number of modes that exist for it to couple to. All right? So there's sort of a trade-off. And eventually, of course, the exponential will always beat the polynomial, right? So you sort of see this behavior. This is a theoretical curve for gamma up. This is 1 over gamma up. This is the relaxation time, where it gets worse first. So the process gets fast. So you would expect your spin to get worse. And then it starts to get better very fast, okay? And this curve, in theory, should determine the spin coherence on the lower branch. Another thing that's sort of instructive to look at, but it's not going to be useful for what I'll talk about next, is this process gamma down, which has a completely different behavior. So gamma down has a component that's determined by thermal excitations, but even if you increase the splitting to very large values, you will still have spontaneous emission. That's something you can never fundamentally kill, right? And that spontaneous emission gets very fast as you increase strain because of this delta cubed, right? The number of modes into which your defect can emit a phonon increases a lot. So essentially, the downward relaxation time gets faster and faster as you increase strain. So with this model in mind, we essentially do experiments to basically measure this rate gamma up. And the way we do that is by time-resolved fluorescence. We use a pump probe technique where we pump on one of the optical transitions of the SIV and shove all the ground state population into one of the levels, wait for some amount of time, shine a laser on the same transition again, and see how much fluorescence we get, okay? And based on the recovery of the fluorescence, we can extract the rate of this upward process. And at 0 strain, we measured that this is 36 nanoseconds. So if you remember that 40 nanosecond number, that's where this comes from, right? And now what happens when we apply strain is that we see that there is pretty good agreement with this theoretical curve. We do make the relaxation time fast in this low strain regime. But as far as the spin is concerned, what we're really interested in is this high strain regime where we start to improve the spin coherence. And in order to probe the spin, we use this technique called coherent population trapping in atomic physics. Another name for this is electromagnetically induced transparency, or EIT. The basic idea here is that you essentially shine two lasers that connect your spin states, that is the two ground states, to a common excited state. So the situation that all of us are familiar with is, say, I call these the carrier and the sideband, just because of the way they're generated using an optical modulator. Um, but suppose you just had the sideband. Suppose you just had the second laser and you were sweeping the laser across this transition, which is what we're doing in this experiment. You would expect to see a nice Lorentzian centered around this transition frequency, right? Um, but what happens when you switch on the second laser is that right in the middle of this Lorentzian, there appears a very sharp dip. And this is this effect called coherent population trapping. And this is a quantum effect. And the physics of this effect is that switching on these two lasers essentially pumps these two ground states into a superposition of up and down, which don't interact with light at all. So essentially, the excitation from this laser destructively interferes with the excitation from the second laser, and you get this dark state in between, which doesn't respond to light at all. And the line width of this dip is indicative of the coherence of the two ground states. And that's the key thing that you should look out for. This line width is what's going to determine the spin coherence. And what we're going to do now is measure this line width as we apply strain. I'm going to skip this part. This is for people who are more interested in details. What I want to show is our final result, and we're still working on theory and everything else to understand this better, is that as we increase strain, indeed, we do see that the line width reduces. That is, the decoherence rate of the spin is reducing. In fact, we see kind of a funny behavior where as we start applying strain, so this is strain increasing from top to bottom, the line width narrows, and at a certain point, it reveals that what we thought was one Lorentzian actually had two narrow Lorentzians hiding within. And because we improved the spin coherence, we're now able to resolve these two narrow Lorentzians. And if we further increase strain, each of those Lorentzians starts to narrow even more. As of now, we think that in our SIV, the one we're studying, this is the effect of coupling to a proximal nuclear spin. We're doing more experiments to understand this, but this sort of physics is kind of well understood with nitrogen vacancies that couple to carbon-13 nuclear spins. But that's something we're looking into in more detail. But the key point is that the line width, as you apply strain, is reducing, and that was the effect that we were hoping to see. We improve the line width to about 170 nanoseconds, and after that point, what happens is that this improvement in the line width starts to saturate. And we understand that this is a limitation of this coherent population trapping technique. If we start driving the spin using microwaves, we can get a truer estimate of the spin coherence. So that brings me to the end of my talk. I'd like to conclude at this point by summarizing. So basically, we did experiments with these cantilevers in which we measured the strain response of the optical and spin properties. And there's the results are exciting because, one, we've measured very large strain susceptibilities. So this is great for hybrid quantum systems in which you want to couple SIVs to mechanical resonators, which is the next wave of experiments that we want to do. This is also great for photonic quantum networks because we can now tune silicon vacancies optically. We were also able to use strain to improve the spin coherence of the SIV. So with that, I would like to thank my team members, in particular Young-ik, who is also part of CIQM. And I did all these experiments with him. The CPT measurements were a collaboration with Mete Adature's group, these three people in Cambridge, UK. And also I'd like to thank Alp from the Lukin group, and thank CIQM for providing me this opportunity. Okay, thank you.
What was the final coherence time? I don't know if I saw it.
We're at about 200 nanoseconds right now, but we know that that's measurement limited. And our measurement is sort of saturating that coherence time. So in principle, if we work with these terahertz strained SIVs that I was talking about, in theory, we should approach tens of microseconds. But hopefully we can measure that with microwaves in the future. Yeah. Sorry, could you say that again? Mhm. Okay, so the question was, uh, when we apply strain, do we observe a increase in the line width of the peaks? I assume you were referring to the optical transitions. Yeah, so no, we don't actually. So there are some situations in which at very high strain, we observe that the line width itself doesn't increase, but the line tends to jump around, which is an effect of, I think, voltage fluctuations at the device. So that's what we call spectral diffusion. Um, so for the line that we're using to do the spin measurements, it's not affected by the thermal physics that much, so it doesn't broaden. But there are other optical transitions. I can go back to the figure later. But if you remember the A line, which is like the highest energy line, that becomes very broad when we apply strain. And we understand that from the thermal physics of the defect that I was discussing earlier. Yeah. Yeah. So so the highest strains that we can apply are, I think, approaching 10 to the negative 3. Where most of the time we're operating in like, mid 10 to the negative 4 kind of regime, which is pretty large, I would say. Yeah. Yeah. So the frequency shift, I mean, it's of the order of hundreds of gigahertz to a terahertz. So a useful number to keep in mind is at these wavelengths, zero point 0.1 nanometer is about 50 gigahertz. So we can shift by a few nanometers, which is pretty large. Yeah. No, no, that's way too much of a shift. These are still perturbative changes. Remember, yeah.
We're gonna take a short break. You guys don't go anywhere. We're just gonna change microphones.
Okay. I'm glad to be here and present my recent work. That something. Okay. Can you hear me? Can you hear me? Is it good? Okay. Okay. So now it's good. It's good? Okay. Is it? Hello? Okay. Okay. All right. Okay. So I will talk about my recent work on in-plane optical anisotropy of layer gallium telluride. So my name is Shengxi Huang, and I'm from MIT, Professor Millie Dresselhaus Group. So I think the audience is quite familiar with 2D materials. So 2D materials are very promising for different kinds of applications. For example, I show a figure here showing some potential applications of 2D materials, including some e-tattoo, which means you can attach it onto your skin and the material can actually monitor your health parameters. And also we can make 2D materials into smartwatches, for example, and smart glasses, and so on. And if we look at this electromagnetic spectrum, which I show here, we can see that different kinds of 2D materials actually occupy different ranges in this electromagnetic range. So for example, if we look at this far infrared range, we have graphene, which is very useful in this range because graphene has the plasmonic range, plasmonic frequency in far infrared. And graphene is also a zero bandgap material, which gives it very high electronic mobility, which is on the which is on the order of 1,000. So if we look at the other end of this electromagnetic spectrum, we have the UV range. And in this range, hexagonal boron nitride, or HBN, can be very useful because it has a band gap of around 6 eV, and this is why it's in UV range. And because of this large band gap, hexagonal boron nitride is an insulator. And in between this HBN and graphene, we have some other materials. For example, TMD, or transition metal dichalcogenide. And this is actually a group of material with different kinds of combinations of transition metal and chalcogens. So in this group of material, we actually have the band gap of around 1.5 to 2.5 eV, which is depending on the specific material. And the mobility is on the order of tenths. And because of this band gap, this group of material is very useful in the visible range. And we also have black phosphorus recently, which is short for BP. And we have the band gap for this BP of around 0.3 to 2 eV. And this is dependent on its thickness. And also this BP has a higher mobility than the TMD material, so it can have some potential applications. And this makes BP useful for mid-infrared and near-infrared range. So if we look carefully on this BP, we can actually find it has some very interesting properties. So here I show the top view of this BP structure. You can see it is very similar to hexagonal lattices in graphene. You can see this is armchair direction and zigzag direction. But if you look at it from the side, you can see it's not actually an atomic layer. It actually has some steps in each layer. And this makes BP has some unique properties. For example, it is an in-plane anisotropic material because many of its properties are anisotropic along different crystalline orientations. For example, the mobility of BP for both electrons and holes are higher along this armchair direction. And the mobility along the zigzag direction is only about a half compared to this armchair direction. So the discovery of BP actually enables us to study a lot more anisotropic 2D materials. For example, gallium telluride and tin selenide, rhenium diselenide, and copper sulfide. And these materials can be useful in different applications. For example, this tin selenide is reported to have the highest thermoelectric performance up to now. It has a ZT of around 2.2. And for this rhenium diselenide, it is reported to have very high performance field effect transistor. So today, I will first focus on this gallium telluride. And why are we interested in this gallium telluride material? One of the important reasons is gallium telluride has recently been reported to have a very high photoresponsivity if it's made to be a photo detector in the visible range. So you can see this responsivity of gallium telluride is as high as 10 to the power of 4, which is much larger than most of the other 2D materials, and also some other nanostructures. Also, the response time of gallium telluride is also small compared to the other 2D materials. And this makes it very feasible to make two-dimensional, photodetectors in the visible range. So if we look closely to the structure of this gallium telluride, we can see it's also a layer structure, and it is a monoclinic structure, which is different from most of the other 2D materials we have studied. And also, if we look at it carefully, we can see it has a very low symmetry, which is C2H. The C2H symmetry means it only has 3 symmetry operations in the lattice structure. So the first symmetry operation is the 2-fold rotational axis along this y direction. So if you look at this line of atoms, this constitutes a 2-fold rotational axis. And the second symmetry operation is the mirror plane. So if you look at it from the top view, you can see there is a mirror plane. And this applies to this structure here. And because we have 2-fold rotational axis and a mirror plane, we naturally have inversion symmetry. So these are the three symmetry operations. And this gallium telluride also has direct band gap of around 1.7 eV. And this is advantageous because the direct band gap occurs from few layer to all the way to the bulk. So this is different from some of the other 2D materials like MOS2 because MOS2 only has direct band gap at monolayer. And starting from 2 layers, the gap becomes indirect. So this makes gallium telluride more interesting for applications. And also, if we look at the unit cell here, we can see there are 6 gallium atoms and 6 tellurium atoms in a unit cell. So in a total of 12 atoms. So this makes its structure a little bit more complicated. So if we look at this one, this is the first Brillouin zone of gallium telluride. We can see the structure is quite complicated, and there are several high symmetry points shown here. And we can use DFT calculations to calculate the energy band structure. So we can see roughly along this line, the bands are quite flat, and this means the optical absorption can be quite high in this band gap range. So if we look at the vibrational modes of gallium telluride, we can see there are a total of 36 vibrational modes. And through calculation and analysis, we know 18 of them are Raman active, which means we can measure them using Raman spectroscopy. And for these 18 Raman active modes, 12 of them are AG modes, which means the vibrations of these modes are totally symmetric. And the other 6 of them are BG symmetry, which means there is one dimension which is asymmetric. So as I mentioned before, gallium telluride has in-plane anisotropy, and potentially we can use RAM. Yeah. Mm-hmm.
So is there any intuitive understanding as to why we get these flat bands? Like what is it about this material that gives these flat bands?
Yeah, so this result is through calculation, and I think maybe part of the reason is the interaction between each atoms in a unit cell can be very strong, and because we also have a total of 12 atoms in a unit cell, which is quite big, this might makes it has a very flat band structure. Yeah. 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 So yeah, I'm about to talk this. So because I mentioned gallium telluride has in-plane anisotropy, and we can potentially use Raman spectroscopy to study this in-plane anisotropy, because one important issue if we encounter a material with in-plane anisotropy is how can we determine the crystalline orientation if we have a flake of this material. And potentially Raman spectroscopy is a very convenient tool because it is non-destructive and it's very fast. So in order to study Raman, we need to know how many vibrational modes are there. And we need to know the symmetries of these vibrational modes, because different symmetries can give us different anisotropy of the Raman modes. Yeah, so I will talk about this in detail later. Yeah, so Raman spectroscopy, if I think maybe most of you are very familiar with, is a technique discovered about 90 years ago, and it actually describes the inelastic scattering of the incident photon onto the material. So for example, if you look at this figure, for this elastic scattering, the scattered photon and the incoming photon has the same energy, and there is no energy transferred to the material. However, for Raman process, we have inelastic scattering, which means the outcoming photon has a different energy than the incoming photon. And this energy difference is transferred to the lattice, which causes the vibrations of the lattice. So if we measure Raman spectroscopy, we can see there are several peaks, and each peak represents a certain vibrational modes. For example, this one is a methane molecule, and you can see different peaks represent different vibrational modes. So using Raman spectroscopy, we can first measure gallium telluride. So here is the experimental results, and here is the calculation. We can see in the experiment, we can observe in a total of 8 Raman modes. And here we can see 2 very broad peaks and very high peaks, which is around 126 and 142. And these 2 modes are the double resonant or second order modes of Raman. And also we can see there is a peak for 161, and this is a BG mode, which has a different symmetry than all the other peaks, because all the other peaks we observe are AG modes. So from experiments and calculation, we can see all the 8 modes that we observe in the experiment can be predicted by the calculation. And further, we can study the polarized Raman. Because as I mentioned, if we measure polarized Raman, we can potentially tell the crystalline orientation of the gallium telluride. So here I show the Raman spectrum with different polarization of the incident laser. So you can see from 0 degree all the way to 180 degree, the peak intensities can be changed. So here over here, I show the Raman intensity polar plots for all the 8 Raman modes we have observed. So you can see this is 0. So for example, for this 107 inverse centimeter Raman peak, we can see the highest intensity is along 0 degree, or it corresponds to x-axis of the crystal. And the minimum intensity corresponds to 90 degree, or y-axis. And for different modes, we can see their Raman anisotropy is different. And also, for the same flake we measured on Raman, we also did TEM diffraction pattern. And because TEM diffraction pattern is a very definite way that we can tell the crystalline orientation. So it's shown here. You can see this horizontal axis corresponds to x-axis from this diffraction pattern. And therefore, you can see it corresponds well to the Raman anisotropic Raman intensity. And therefore, we know that potentially Raman can be used to determine the crystal orientation. But it is, in fact, it is more complicated because we have measured Raman with different incident laser wavelengths, including 532 nanometer, 633 nanometer, and 785 nanometer. And we also measure Raman on different flakes with very different thicknesses. So we observe that Raman anisotropy can actually be quite intricate in gallium telluride. So let's first look at these 3 polar plots. So these 3 polar plots are for one flake for this 107 Raman peak, but at different excitation wavelengths. So we can observe that the Raman polar plot is oriented differently for different incident laser wavelengths. So this 532 nanometer laser, the Raman polar plot is is vertical. So the maximum intensity is along 90 degrees. However, for this 633 and 785 nanometer laser, the maximum intensity is along 0 degrees. So these plots are totally different with each other. Yes, yes. Oh, yeah. So the question was, is the incident angle the same for all the 3 flakes, for all the 3 lasers? The answer is yes. So the measurement condition is totally the same, except for this laser wavelengths. So this is the first observation. And the second observation is the Raman anisotropy can also strongly dependent on the phonon modes. So as we can see here, these 3 modes gives us very different Raman polar plots. So for this 107 mode, we know it's an AG symmetry mode, and therefore we can see the period of this Raman intensity is 180 degrees. However, for this 161 mode, which is a BG mode, it has a different symmetry than this 107 mode. You can see the period is 90 degrees instead of 180. And also for this 280 modes, it's also an AG symmetry, the same symmetry as the 107 mode. But you can see their Raman orientation is also different. So from this, we can know that the Raman anisotropy is also dependent on the phonon modes, including both the phonon symmetry and phonon frequency. And also, if we look at the Raman anisotropy for different flakes, here I show a relatively thin flake, which is still very thick. It's about 60 nanometer thick, and an even thicker one, which is around 130 nanometer thick. We can see the shape of the Raman polar plots are different, but overall the orientation are the same. So we cannot see the polar plot has different or the opposite orientations for thin and thick flakes. So from this, we know that Raman anisotropy for gallium telluride is strongly dependent on the laser energy and the phonon modes, but weakly dependent on the flake thickness. And these phenomena can actually be explained using the optical transition selection rule. So before I explain the optical transition selection rule, I also want to show you some of our results on optical absorption. So we also measure optical absorption using the incident light with different frequency, different polarizations. So we always observe that the optical absorption along 0 degree, or when the incident light is polarized along x-axis, is a little larger than the 90-degree polarization. So as you can see here. And also, but you can see this difference is not that much. So actually, if we also plot the polar plot of the optical absorption, we can see this anisotropy is quite weak. So we also measure this for flakes with different thicknesses. You can see here, this figure, the y-axis shows the ratio between x and y absorption. So you can see this ratio is actually quite small. If the flakes are thicker than about 60 nanometers, we can see the ratio is actually approaching to 1. So this means the optical absorption anisotropy is quite weak in the visible range. And we have this result compared with BP, or black phosphorus. As I mentioned before, black phosphorus also has in-plane anisotropy. So we also did the same measurement on BP. So you can see this BP optical absorption anisotropy is actually quite large. You can see this this polar plot has very clear preference towards 90 degree, and the minimum absorption is along 0 degree or zigzag direction. So here we have an interesting comparison because we can see here that the optical absorption anisotropy for gallium telluride is quite weak compared to BP. However, if we look at the structures of these two materials, we know that gallium telluride actually has a lower symmetry than BP because BP has a D2H symmetry compared to the C2H symmetry than gallium telluride. But the optical absorption anisotropy is opposite for their structural symmetry. So from this, we know that we cannot just predict the optical anisotropy according to its structure, and this is actually dependent on their energy band structure. So with this, I would like to explain the optical transition selection rule, and this actually can explain why we observe the optical absorption anisotropy and the intricate Raman anisotropy. So first, let's look at the band structure of gallium telluride. So we know there are several energy bands shown here, and for each energy band at each high symmetry point, we can have different symmetries for these electron wave functions. So for example, if you look at this band at Z point, you can see its symmetry is Ag. But if you look at it, look at this one, it's Bu symmetry. So we can calculate this using DFT calculation. And now, if we want to have optical absorption, which is an electron-photon interaction, we need to observe, we need to have two conservation rules. The first one is energy conservation, which is easier to understand. This means that the initial state of the electron will absorb a photon and be excited to an excited state. And the energy difference between this excited state and the initial state has to be equal to the photon energy. So this is the energy conservation. We also need to obey the symmetry conservation rule, which is the second conservation rule, and which means, for example, if the electron from this Ag state wants to absorb a photon and be excited to this Bu state, the symmetry of this photon has to be Bu state, which means the polarization of the incident photon has to be along X has to be X polarized. And actually, if it's not totally X polarized, it will still have absorption, but the absorption is much weaker. So if the incident photon is along Y direction, then there is no absorption at all. So this is the Ag to Bu state. As you can see here, the optical absorption polarization polar plot can look like this. And on the other hand, if one electron from this Bu state wants to be excited to this Bg state, the incident photon cannot be along x-axis, and the maximum absorption can occur when the polarization of the photon is along y-axis. So therefore, you can see a polar plot like this. So actually, in the visible range, according to our calculation, all the optical absorption should have the case like this, which means the optical absorption is preferable towards 0 degrees or x-axis. And this is the calculation result we have. And that explains why for almost all the flakes we have measured, the larger optical absorption can happen when the incident light is along x-axis. And now let's look at Raman. And Raman is more complicated because Raman process has actually three processes. The two of them are electron-photon interaction, and one of them is electron-phonon interaction. So here's the process. There is an electron in this initial state, and this electron will first absorb the incident photon and be excited to an intermediate state, like here. And then this electron in this intermediate state will scatter with the phonon, which has electron-phonon interaction. And this electron will be relaxed to the second intermediate state, as you can see here. And the final state is this electron in the second intermediate state will emit another photon and be relaxed to the initial state. And this is also electron-photon interaction. So we know there are three processes. Two of them are electron-photon interaction, and one of them is electron-phonon interaction. So let's look at, for example, Ag Raman here. Yeah.
So can you remind me or tell me what the Raman shifts are in frequency units? I know you
Yeah. Yeah, so the Raman frequency corresponds to the energy difference between these two intermediate states. So they are roughly around 100 inverse centimeter, which translates to about around 20 millieV. Yeah. Yeah. So let's look at this Ag Raman. So for Ag Raman, because Ag is a totally symmetric phonon mode, so the two intermediate states should have the same should have the same symmetry. So therefore, we have the first electron-photon interaction shown here has the x-polarized light, x-polarized orientation. And then we assume that this electron-photon interaction has no polarization dependence. And the final state for the electron-photon interaction, it also has the same polarization. And then the products of these three terms give us a x-polarized AG mode Raman anisotropy. So actually, if this electron-photon interaction is towards 90 degrees, we should have the AG Raman modes towards 90 degrees. But no matter what polarization it has, the observation is it has a period of 180 degrees, as you can see here. So if we look at this BG Raman, which is asymmetric Raman mode, we can know that the two intermediate states here should have different symmetry. And therefore, one of the electron-photon interaction has the polarization along 90 degrees, and the other one has the polarization along 0 degree. And the product of them give us this shape, which has 90-degree period. So that's why for the BG Raman, we can observe the period is 90 degrees for the Raman polar plot. So so this corresponds to this 181 inverse centimeter Raman modes because it has BG symmetry. So for all these measurement conditions, we can observe a 90-degree period. And for the other Raman modes, we can observe the 180 period. So next, we study the interference effect because as you probably observed that for the calculation, the anisotropy seems to be very large because this 0-degree absorption seems to be much larger than this 90-degree absorption. But if we consider the interference effect, which is due to the permittivity difference for gallium telluride along x-axis and y-axis, we can actually reproduce the experimental results pretty well, as you can see here. So this is the calculation absorption, including the interference. We can know this anisotropy is much reduced, but still we have a larger absorption for 0 degree than the 90-degree case. And if we consider the interference effect for Raman measurements, we can see it actually cannot reproduce our experimental results because if you look at this one, this is the enhancement factor or the Raman intensity along y-axis and x-axis, and this is the ratio of them. This calculation results only consider interference, and therefore we can see for 532 and 633. The y-axis Raman always has a larger intensity than x-axis Raman. But this is apparently not the case for our experiments. And therefore, we know that interference effect cannot explain the Raman anisotropy. So the Raman anisotropy is largely due to the anisotropy of light-matter interactions, as I explained before. So if we, so here I show some more materials with in-plane anisotropy. So this includes black phosphorus and gallium telluride, as I introduced before. And this also includes rhenium diselenide, rhenium disulfide, which has space group of P1 prime, P1 symmetry. And also it includes some 1T prime phase of TMD materials, as you can see here. So as I mentioned before, this optical absorption transition rule can also be applied to these materials with the in-plane anisotropy. But when we study these materials, we need to be extra careful if we want to use Raman or optical absorption to determine the crystalline orientations of these materials. So here I show an example of rhenium diselenide and rhenium disulfide. So you can know that these materials also have very low symmetry. It only has one inversion symmetry. and we can see this Raman, and this polarized Raman has anisotropy along different polarization angles. And here is our work on BP Raman. So we can see that black phosphorus, or BP, has 3 Raman modes. So this is AG1 and AG2, which are both of AG symmetry. And we also have B2G modes, which is a different symmetry than this AG modes. And therefore, according to our analysis before, we know that BG mode has a period of 90 degrees. And for these 2 AG modes, they have the period of 180 degrees. And here I show a very direct example of why we should be very careful when we try to use Raman to determine the crystalline orientation. So here I show 2 flakes with which we measure TM diffraction pattern. So we know this horizontal axis is zigzag and vertical axis is armchair for both flakes. However, if you look at the flake on the left, you can see that the maximum intensity for AG1 and AG2 modes are along 90 degrees. And for the flake on the right, the maximum intensity of AG1 and AG2 modes are along zigzag direction. So this is a very direct evidence to show that Raman anisotropy is intricate. So actually, we can study more flakes. So here in this set of examples, I show some flakes which are connected together, which means they have the same crystalline orientation. However, the different colors show that they have different thicknesses. So if we measure Raman anisotropy for all these flakes, we can know how the Raman anisotropy changes with different thicknesses and as well different excitation wavelengths. So we can observe very clearly that the Raman anisotropy is different for different excitation wavelengths and different for different thicknesses. And actually, we have measured, so actually we have measured more flakes. So in this table, for each row represents 1 flake. And if the rows are of the same colors, which that means they have similar thickness. If the rows are of different colors, that means the thickness are different for them. So let's first look at these 3. So this is the similar case as gallium telluride. So we know that different excitation wavelengths can give us different Raman anisotropy. So you can see very clearly for this 532 nanometer excitation, the Raman polar plot is towards roughly 30 degrees. And for this 633 case, it's towards 120 degrees. And next, if we look at this, if we look at these 2, we know that for flakes with different thicknesses, the Raman anisotropy can be different. And this is what we didn't observe in gallium telluride, because the flakes we studied in gallium telluride are mostly very thick. But in this case, if we compare this, for example, 20 nanometer case and 40 nanometer case, the Raman polar plot can be quite different. And actually, if you look at the flakes for the same thickness, you can observe that all the Raman polar plots are the same, are of the same orientations. But if the thicknesses are different, or if you look at the flakes with different colors, you can see this Raman polar plot can be different. So this is a direct evidence to show that the thickness also matters for Raman anisotropy. And also, since we have 2 AG modes here, we can see these 2 AG modes can also give us different Raman anisotropy. And this is what also what we have observed in the gallium telluride case. So here is the optical absorption for BP. So no matter how Raman anisotropy is intricate, we always observe the maximum optical absorption of BP along 90 degrees or armchair direction. And but for the Raman case, they can be different. So this tells us that if we want to determine the crystalline orientation of BP, the best way is to use Raman is to use optical absorption, because the maximum optical absorption always occurs for armchair direction. And all these phenomena can also be explained using the optical transition selection rule I have explained before. So with that, I would like to conclude my talk. First, I show you that gallium telluride is a 2D material which is promising for optoelectronic applications, especially in the visible range. And gallium telluride has in-plane anisotropy, and therefore we can use polarized Raman to detect the crystalline orientation of gallium telluride. However, this Raman anisotropy can be quite intricate. So it depends on the laser wavelength, the phonon frequency, and maybe also thickness. So this anisotropy can be explained using the optical transition selection rule. And actually, this optical transition selection rule is universal for almost all the 2D materials with in-plane anisotropy. So with that, I would like to thank my advisor, Professor Millie Dresselhaus and Professor Jing Kong at MIT, and all my collaborators, as well as my lab mate. So this photo was taken at Millie's 84th birthday party. And yeah, so I would also acknowledge the funding support from NSF and DOE, and I would like to thank CIQM for this opportunity, and thank you.
Any questions? That's awesome. I'm very impressed by the broad range of data that you have amassed on these complicated crystal structures. I don't have any real questions except for congratulations. There's a lot of effort there. So,
Yeah, thank you.
Thank you very much.
Thank you.